Thanks so much for the introduction. So yeah, today I would like to talk about how to train vision models to billions of parameters and scaling them to billions of parameters and being trained completely unsupervised on trillions of tokens or patches. So whenever we tackle like a problem with machine learning, we're trying to optimize some metric like accuracy, perplexity, or any other metric. What we hope for is that as we scale the model parameters more and more, and as we scale the training data that we train on, we can see consistent improvement in performance. This has been the case for large language models, and this has been the main reason actually why I've been so successful and very rapid improvement in performance. So the Scaling Laws paper tried to actually tackle exactly that, how to predict like the improvement in performance by how we scale or invest more in scaling with parameter size or with the data size. And with this actually like in mind, as people started like realizing that this is the case, that we can actually simplify our methods and scale them aggressively, this has been started raised to the top with large language models. With every year, we're scaling models more and more. And eventually this led to the ChatGPT method model and Llama, Gemini, and now like a million other LLMs. And to summarize, like why this happened is that we have models that scale well in terms of parameters, that scale well in terms of data, and most importantly, actually also unsupervised, which allows us to create a lot of data from like web scale data. So for LLMs, we create data from the web with very maybe gentle filtering, and we can scale and train on enormous amount of data without any curation or annotation efforts. So now the question is, these like constraints or these properties, how much are they're already there for like vision models or like methods that train to learn vision features. So still like supervised learning is a very popular method. People still work very hard on training on ImageNet and other methods. And if you look from maybe this plot from the MAE paper, they argue that actually if you only rely on supervised learning and you scale the model parameters from maybe 80 million parameters to 600 million parameters, you see only very marginal gain in performance. And this is using the ImageNet dataset. Now, if you are lucky enough maybe to work for Google and you have access to the dataset like JFT, which is semi-automated labeled dataset of like billions of parameters, billions of labels, you can maybe train larger models and you can see some gains. But even as they scale to 22 billion parameters, we started seeing more diminishing returns. So scaling from the E model to the 22B, which is like 5.5x larger, we only started seeing marginal returns. So in that sense, we believe that supervised learning methods do not scale very well in terms of parameters. They could scale well in terms of data. However, it's extremely expensive to get that, and it's very cumbersome to invade all these amounts of data. And obviously, they are not unsupervised. Now, if you look at other really popular methods like the DynaV2 or the joint embedding methods in general, we have this like very famous table in the DynaV2 paper, which needs tons of tricks, so many things actually to make it work well. It needs like an EMA teacher, it needs schedules for the weight decay, schedules for the momentum, schedules for everything actually to function well. And while the performance is extremely good, it's very brittle. It's very hard to scale and very hard to push further. So in that sense, it's extremely challenging to scale in terms of parameters. On the other side, if you look at data, joint embedding methods rely on this invariances for different transformations, including cropping, which is the most important one. And if you look at the results for the performance from uncurated data to their own in-house curated data, you see big drop in performance. So again, like they're very sensitive to the type of data they can be trained on, and therefore you cannot just curate images from the web and with gentle filtering and just train on them. So again, here, scaling in terms of data is very challenging. Now, if we go to methods like mass code encoders, I think it's definitely a great step in the right direction. So of course, it's unsupervised. It relies on this patch dropping mechanism, which makes it very, very efficient to train. So actually, the scaling in terms of parameters is very easy. We can scale to very large parameters and train quite efficiently. However, many studies show that MAE suffers from this problem of not able to use more and more data. So as actually, for this paper, this plot, we show that if you scale from pre-trained data from infinite 1K to 21K, so roughly 12 to 14x larger, you see almost no gains in performance. And this is like a matter of like all mass code encoding methods, including BERT, has this problem of they're under like a severe underfitting regime, such that it's very hard to be a good sponge for data sets. So it maybe it's kind of disadvantage is it's very hard to scale in terms of more and more data. And finally, maybe one of the most popular methods and most successful methods in scaling is CLIP. So it's not unsupervised. However, it's definitely easier than the completely supervised method since we rely on noisy labels. In terms of data, actually, they scale very well. So we have been a lot of efforts, and a lot of the recent wins in the last years have been coming from datasets like Lion, Datacomp, and others, where we're scaling to 2 billion images or 5 billion images, and we have been seeing more or less consistent gains in performance. However, like the parameter scaling is yet to be seen. So I think there's no clear argument why it doesn't scale in terms of parameters, other than the lack of very good models beyond 1B model. And it's unclear actually what's the problem with that. Like, for example, if you look at the OpenClip models, as you scale from like large to huge to 1B, the gains are not very large, and we don't have many stronger models that are beyond the scale. Okay, so with that, the question is, can we find a method for pre-training and computer vision for training good features that satisfies all constraints? Like, it's unsupervised, so we can train on potentially uncreated sets of web images and scales well both in terms of parameters and in terms of data. And with this, actually, that's the question we try to answer in our paper, which is like we call AIM for autoregressive image models, and this will be presented at ICML next month. So autoregressive models in general can be applied for vision, can be applied for text, which we hear like, and it's this instantiation of it that we use now in machine learning, where we try to predict the next token. So we can have some number of tokens as the input of the model, and the model is trying to predict the token next to it in position. Very simple recipe. And they have been used very heavily in vision. And like since the Pixel CNN and other methods, but now even for like image generation, it's one of the most popular methods and one of the most effective methods alongside diffusion. And since the VQVE has been very strong, we have examples like DALI, Party, VQGAN, and others that are very strong. However, all these generation methods rely on discretization using like maybe VQGAN, like VQ, vector quantization, or other methods. And if you like the few methods that try to probe the representations, we find them actually very weak compared to other methods that are dedicated to learning representation. And maybe one of the most famous or like the most popular ideas of like exploring how well would autoregressive methods do for representation learning. So the goal of this paper, the IGPT paper from OpenAI in 2020, was actually to use autoregressive pre-training for representation learning, not for generation. However, this was like a pre-vision transformer paper. So at the moment, they used only 32 by 32 images or something slightly higher. And the autoregression was happening over pixels, not over patches. It showed actually strong performance for the large models, but it was like orders of magnitude larger than their peers for the contrastive methods like SimCLR. However, one of the actually most interesting plots in this paper is that they show that as you actually get better at the pre-training task, which is the validation loss, maybe perplexity for the next token prediction, you get consistently better at the representation task for like linear probe in that sense. And how you get better actually at the validation loss is via training for longer. So it's the same plot going right, or making the models bigger. So we have a glimpse of a method that actually scales well in terms of data and also in terms of parameters. However, at this scale, it was very overly parameterized for the performance it was given. So one of our goals is actually to revisit this basic recipe, a basic problem of autoregression for image models, and add all the necessary components to actually make it competitive with state-of-the-art methods at the moment. So first, we use a bit style patchification. So we have an image, we have like 14 by 14 patches, and we patchify the image into patches like this. Afterwards, after we have this patches, we need to unravel them in a different, like in a certain sequence. So we use like a raster order, row measure order. Afterwards, we just feed it to a causal transformer, so a transformer that has a causal attention, exactly similar to LLMs. For the prefix part, I will discuss it more like later, but for now, we can assume it's just a simple causal attention transformer, identical to the ones we use for decoder-only LLMs. Afterwards, we have an MLP that's applied per patch. So every patch has an MLP on top, and then we do very simple next token prediction, and pixel space. So we do MSE or regression loss to predict the pixels for the next token. So we intentionally try to make the recipe as simple as possible and actually as close as possible to the LLM recipe to benefit from the same scaling advantages. One very important thing is that actually how to measure progress. So if we want to see the performance or probe the performance of our models, the most popular method now, or the thing that people rely on, is linear probe. So we just maybe do a global average pooling of the features, and then we learn linear classifier on top, which works extremely good for contrastive methods that has been trained actually on a very, very similar task of telling things apart, telling positives from negatives. So it's very easy for it to do this. However, a very simple modification of doing attentive probe, which has been adopted recently with more and more works, we only need to add 2 extra matrices, like keys and values. And what we learn here is more of a weighted average than an average uniformly across patches. So with this extremely simple modifications, but it can have a very large impact on methods that are not trained similar to contrastive methods to tell things apart and very well aligned for linear probing. So if you look at this, actually, if you look at method like Dino, and you look at the performance between the difference in performance between linear probe and attentive probe, something that learns the weights for mixing the patches, we see only some small marginal improvements. But if you look at something like AIM, which is a generative method, so it learns to generate patches, so it's not, during pre-training, it's not aligned to have good descriptors. We see that there's a huge difference if you do linear or attentive probe. And now if you do attentive probe, it is actually a competitive method. So our assumption that, for example, mask coding encoders were much, much weaker methods compared to contrastive methods might have to do with the fact we were looking at the wrong metric, because attentive probe keeps the same probe, good properties of linear probe. It's very, very lightly parameterized. It's very hard for it to overfit, and you can learn this classifier on top with no problems. And our observation actually also extends to ME, so that we see the exact same thing with ME. So we think this is something general for generative methods that are trained this way. If you want to probe the representations and know it's good or not for recognition tasks, I would advise using an attentive probe rather than a linear probe. Okay, so now we go back to the prefix part that I skipped before. So at the moment, as I mentioned, we train with some tokens. We pass through a causal transformer, and we predict the next token. So pre-training is causal, so every token only sees the previous tokens in the sequence. However, usually for computer vision, we would like to evaluate our models bidirectionally, similar to VIT. VIT is not causal. VIT has bidirectional attention, and there is no reason for images to be evaluated with causal attention. It's a bit unnatural for it. However, if you do this, the method doesn't work at all because it has not been trained on any bidirectional attention. And therefore, you need to use a causal attention actually to get any performance that is good. However, we found that actually there is a workaround. There's something we can do, which is revisiting the prefix LM idea from the T5 paper. And the idea is very simple. We basically pick a prefix length, so from 0 to some length in the sequence that is sampled randomly, uniformly from the sequence length. And we say that this prefix, we will do the attention here bidirectionally. So we will not do causal mask, we do bidirectional attention. And then for the rest of the sequence, we do causal attention as usual. And we only measure the loss over the causal part. And with doing this kind of uniform sampling, we see all types of sequences, all types of length that see bidirectional attention. And with this, actually, we can, without any adaptation, go to bidirectional attention evaluation while not needing to do any adaptation or any fine-tuning to make it work bidirectionally. And if you look actually at the numbers, if you train with a causal attention and then use it in bidirectional mode, you get 52% on this attentive probe benchmark. But if you do prefix and do bidirectional, actually you get a much, much stronger performance, more than 20 points gain in performance. So this method actually has been very effective. And what we find that actually during inference, the method works almost as good causally or bidirectionally. So if your application needs causal attention during inference or during downstream, it also works in a causal mode just perfectly fine because in the prefix it has seen both modes. Okay, so now we go back to the initial question of scaling. So we actually scale these models from 600 million parameters, which is equivalent to the bit huge, to up to 7 billion parameters, which is relatively new for vision models. We don't typically scale them this much. And I don't know if you see the resemblance, but this plot looks somewhat similar to the Llama plot. And what we see is that as we train, make the model larger and we train for longer, we see very clear improvements in terms of the validation loss that we measure for the pre-trained task. At the same time, we see this actually mirrors it, a very similar improvement in the downstream task. So if you look at the ImageNet top one accuracy, we see a clear improvement in terms of the top one accuracy as we scale the models higher and higher. This is like just a similar view to the same thing, a different view for the same thing, which is we look at the x-axis, how when the validation loss is going down, and as the top one accuracy over 15 different benchmarks, which does not just not ImageNet, 15 different benchmarks, the average, and we see how the performance improves as we scale models more and more. So here we see like a very, very clear improvement and scaling, a good scaling behavior in terms of parameters. And one actually of the most interesting thing, I think the most practical thing is, unlike Dino, unlike all other methods, we don't need any tricks to do this. We don't need a stochastic depth. We don't need layer scale. We don't need query and key layer norms. The method is extremely stable, and we scale up to 7 billion parameters with no effort. Like we just make the model bigger, wider, and just hit run, and actually it worked from the first attempt. So it has very similar behaviors to LLMs. As long as we can actually know how to optimize LLMs up to the scale and higher, we have seen no issue with this, and we have seen no saturation in terms of scaling. Now, when we talk about data, for all, like, I would say the majority of the self-supervised learning methods like Dino, MEE, and others, what we can see is that they rely on image network training. And again, our main objective was that to go beyond this, to have like more coverage to all types of data. And it doesn't need to be just object-centric, dogs and cats. Like, we want to go something like more scale, like higher scale than this. And for this, we use the DFN, like the data filtering network dataset that has been created for CLIP. But here we only use the images. So the curation here happened just by matching the image and text pairs, but there's no curation happening on the image side. And we only use the image in this sense. And what we see is that moving from 1 million to 100 million to 2 billion, so the scale here is log, we scale log linearly in terms of data. So we see a consistent scaling in terms of data as well. And I think more importantly, is an uncurated set of data. Or maybe like if you look at it's maybe some filtering based on the text, but the images themselves, we don't say, oh, we want ImageNet like images, or we want very particular type of images. We have all types of images, including like screenshots, matplotlib, plots, everything. Now, if we look actually at what happens if you train with ImageNet, so our model, unlike ME, and unlike the Dino and other methods that are very heavily regularized, our method is similar to LLMs. It has a lot of capacity, and we scale it largely. So if you train on ImageNet, actually you see an overfitting behavior. So you get good very fast, but then you saturate and then actually get worse. If you train only on DFN, and now we're measuring the validation loss on ImageNet, you see a consistent improvement. Of course, it's not overfitting because at this point, we're only seeing every image once. There's no epochs. So we're only seeing every image once. However, because of the domain gap, the loss is still higher. And we find that if you do like a mixture similar to LLMs, where we upsample Wikipedia, like the clean set, we upsample it. In this case, the DFN to be plus is 80% of the time we sample from DFN, and 20% of the time we sample from ImageNet. And we see that actually beats both. This gets the best of both worlds. We scale without overfitting, and we have a very good coverage. We also try to see potentially like a very like small glimpse at scaling loads. So we wanted to see what happens if you spend your compute differently. So now we scale well in terms of data, we scale well in terms of compute, but which way should we spend our flops? So we see that training with a 1B model, we get certain performance on the validation loss. As you make the model bigger, 3B, it gets better. 7B, it gets even better. And now if we decide to spend our flops differently, so scaling from seeing 2B images to 5 billion images, we see a very interesting thing. We see that actually roughly around the same number of flops, we get also the same number of almost the same validation performance. So the 1B model that's trained for 2.5 times longer gets roughly the same validation loss as the 3B model trained for almost half the time. And this repeats. So we also see that the 3B model trained for longer gets roughly the same performance as the 7B model trained for half the time. So that was an interesting scaling loads-like behavior. And I think we need more effort to see which axis should we actually invest more in, which axis is more effective in investing in. And then there's like some basic questions, I guess, that like in the beginning we mentioned to use raster order, but like raster order is just something people have been using. It doesn't need to be the pattern that we use. So on the left, the top left, we see like how we do kind of row measure and unraveling of the sequence, but we can do other things. We can do, for example, like I think intuitively we thought spiral inside out would make a lot of sense. So we start from the middle of the image and you spiral out. And we thought this has a very good intuition about you look at the image in the beginning and you zoom out until you like outpaint. You keep outpainting outside, and this is a more of like a reasonable bias for images. Also tried some like checkerboard patterns. We tried sampling a pattern randomly and fixing it and using it for all the training and tests. And interesting, what we find is that raster is still the best. So raster order performs best, spiral second, checkerboard third, and so on. And we wanted to find, is there any good reason why raster is good? Like raster is very arbitrary, and we wanted to know why is it maybe potentially good. So we tried to look at how actually the loss evolves as we go more into the sequence. So intuitively, again, as you have more and more context, the task gets easier and easier. And we wanted to see how the task, like distribution of the difficulty across the sequence. And what we see that is like the more uniform is the difficulty. So like if the difficulty is maintained across the sequence, the better the performance is. So raster in relative terms is the most uniform. So the task remains difficult from the beginning till the end. Spiral is slightly less uniform. And then you get to checkerboard, which has like very interesting, it keeps being very hard, you keep jumping. And then after you finish the first round, every patch has neighbors. So now it gets very easy. So I have a step drop in the loss and then it gets easier. And I think the working intuition that we have is that you need the task to be as uniformly difficult as possible during training. So again, one other thing that is well known about generative models that it's not well tuned or not well aligned to have good descriptors for the image at the end. It's just trained to generate the image. So there's no reason for one particular feature at the end of the model to be very good in representation or very good in terms of a descriptor. So we try actually to see what happens if we do that tentative probe in different layers after pre-training. And what we find is kind of expected is that actually the last layer is not the best. We don't see like a very harsh drop in terms of performance as we go deeper because of the MLP that we added. However, we see still like the best performance is roughly between half and 2/3 of the model depth. One of the more interesting applications now of vision models is VLMs, so like vision language models, and using it with LLMs. And there's this paper, I think, called MM1 from our colleagues at Apple that used vision encoders and fed them to an LLM through concatenation and then doing self-attention and then doing the same tasks of in-context learning and few shots in context learning. And then we'll try to look at the vision encoder, what happens if we replace the vision encoder that typically is a clip model with our clip model, with our AIM. And we see that clip, that actually is the state of the art for this task, gets 61.4 on few shots, 8-shot exact accuracy in context learning. We see that equal capacity of AIM gets only slightly worse, given that it has not been trained with any text. So clip has been trained with both image and text, is language grounded, while AIM has been completely unsupervised. And again, to argue for the power of scale, what we see is that as you go to the 1B, you get actually quite a bit better performance, and you go to the 3B, you get even better performance. So this is a very simple recipe, very easy to scale. It's not even grounded in language and actually works quite effectively with state-of-the-art clip models for the VLM use case. One other paper that I want to actually mention is from like the people at Berkeley from and others colleagues, which actually also looks at the autoregressive pre-training, but for the different tasks. So they're not trying to learn representations. They're trying to solve tasks of reconstruction. So any task that can be solved by reconstructing an image, including in painting, colorization, segmentation, and others. And actually, they show very, very interesting behaviors of in-context learning with vision, which is something relatively new. Where here, for example, they have anything that's not marked by the red is just examples in the context of, if you see this image, I want you to return this label, which is this kind of pose, and you see a few examples of them, and then you give it a test image, and you expect it to actually follow the instruction and solve the task in the same way. And it's an early version, but I think it's very convincing that the in-context behavior is also doable in vision, and an autoregressive model is a very powerful way to achieve this. So as a summary, we talked about autoregressive models for vision. We provided a very simple recipe with just continuous images in. We don't do any discretization. We have a causal or prefix transformer, have an MLP on top, and just try to predict next token in pixel space. We show a very clear scaling in terms of parameters, very clear scaling in terms of data. We show scaling laws-like behavior where we can spend the compute differently on data or on parameters, and we can predictably get better performance. We showed that it is a very good fit for visual language models, which is one of the most popular applications of vision encoders. And finally, we showed also some examples of in-context learning in vision that is powered by autoregressive method. Our models and code is open source. So we have our methods are up to the 7B model are open source. They are available on Hugging Face on our GitHub repo, and the inference code in JAX, PyTorch, and MLX is available. Thank you so much, and happy to hear any questions. Thank you.